Hello everyone, welcome to our second lecture on graphs. In the first lecture, we gave an introduction to graphs, mentioned their applications and how graphs are represented, and what kinds of problems are solved using graphs. Today, we will start the second lecture on what are called undirected graphs and do what is called the basic traversal of undirected graphs and understand how through this traversal we can solve several problems. Just to recapitulate, an undirected graph consists of two entities, a set of vertices V or nodes and a set of edges E. The set of vertices are connected by the set of edges. For example, in this figure which we have, the figure 1 which we have here, we know that there are so many vertices in this figure. So we are aware that this figure has got the following vertices. There are 9 vertices in this figure 1 and there are 10 edges 0 to 1, 0 to 8, 0 to 3, 1 to 7, 2 to 3, 2 to 5, 2 to 7, 3 to 4, 4 to 8 and 5 to 6. So based on these, we know that the number of vertices in the graph is 9 and the number of edges in this graph is 10. And these edges have no labels. In general, we will use a very important function called the successor function. The successor function, given a node I, the successor function gives the set of nodes to which I is connected. For example, if I ask for the successor of node 2, then I will get node 3, node 5 and node 7. If I ask for successor of node 1, I will get node 0 and node 7. Similarly, if I ask for successor of node 4, I will get node 3 and node 8. This successor function is a function that we will use consistently throughout our programs and our algorithms. The second part is about directed graphs, undirected graphs which are weighted. That means in the figure 2, as you can see, that these edges have weights on these edges. As we have seen in the previous day, these weights can be various labels. For example, in a city map, these nodes can be points in a city and the weight on those edges can be the distance between those points. Similarly, there could be other variables which assign the label or the weight to this undirected edge in a weighted undirected graph. We now come to the important problems that we want to solve in an undirected graph. The first problem is the reachability problem. The reachability problem is as follows. Given two nodes of a graph, we would like to know whether there is a path between them. So what is a path? A path is the sequence of edges between nodes from one vertex to another vertex. For example, if I want to know what is the path between 0 and 8, then there is a direct path between 0 and 8. On the other hand, if I want to know a path between 0 and 5, then here is a path between 0 and 5. There is another path between 0 and 5. There is another path between 0 and 5. And there is a third path between 0 and 5. Therefore, a path is a sequence of nodes which contain edges from one node to another. So it's a sequence of edges between nodes. We also need to remember that there is a slight difference between a path and a walk. In a path, typically, no nodes are duplicated, whereas in a walk, a node may be duplicated. A cycle is a path where you start from one node and return back to that same node. For example, this is a cycle. That means you start from 0, go to 8, go to 4, go to 3, and go back to 0. So finally, a graph which has got no cycles is known as a tree. The other important problem is called the connected components problem. Let us look at this figure here. This figure here, you will see that there is no path from this node to this node. Since there is no path from this node to this node, therefore this node is not connected by a path in this graph. So all nodes which are connected by a path form a connected component. And in this graph, we will see what are our connected components. If we notice, we will see that this part is one connected component. This part is a second connected component. This part is a third connected component, and this node alone is a fourth connected component. So how do we find connected components in a graph? Then there are more complex problems which are called the bi-connected component, the spanning tree, the shortest path, the maximum flow, the vertex cover, the edge cover, the traveling salesman problem. For example, if we go to figure 2, we will see that here is the issue of a shortest cost path. Whereas in figure 1, if we want to know the shortest length path from 0 to 5, then we know that this path is of length 1, 2, 3 edges, whereas this path is of length 4 edges. So we would like to find the shortest length path. On the other hand, in a weighted graph, the shortest length path need not necessarily be the shortest cost path if we consider the sum of the edge costs to be the cost of the path. So finding the shortest cost path is an important problem. For example, the vertex cover problem is a problem by which we try to find the minimum number of vertices of a graph that cover all the edges. The edge cover problem is just the reverse, where we try to find the minimum number of edges in a graph that cover all the vertices. So a graph has got many problems, and we will now see how we will be able to address those problems by some simple traversal algorithms. The basic traversal algorithm in a graph is called the depth-first search algorithm. It is a recursive algorithm which has a global variable called visited. The variable visited, as indicated in this variable, this variable visited indicates if a node is visited by the search algorithm or not, and it is initialized to 0. As mentioned earlier, we will also use the successor function, which is the set of all nodes to which the node is connected. So how does this algorithm go? This algorithm works as follows. This algorithm is called at any node I, and let us say it is called at a node. The first step we say is we mark visited equal to 1. And then for every node j, which is a successor node, we check if it is not visited. If it is visited, we don't do anything. If it is not visited, we recursively call this DFS by DFSG. So now let us see how the algorithm operates, and let us find out how the algorithm runs. So initially, we now have the algorithm where, let us say, we call this algorithm at node 0. And let us say all nodes are initially marked visited equal to 0. And if we call this at node 0, then let us try to find out the sequence in which the depth first search traversal goes on. So firstly, by the algorithm, this node, with node 0 will be marked visited equal to 1. Whenever a node is marked visited equal to 1, I mark it by a red circle here. And I also number it. I number this node as the first node visited. Then what are the successors of 0? 1, 3 and 8. So the algorithm will now check whether visited 1. So it will have to, from 1, it will now call, from 0, it will now call 1, 3 and 8, but recursive. So now it will go to node 1. Node 1 we know visited is 0. So it will, since node 1 visited is 0, it will visit node 1. So it will go to node 1 and visit node 1. So it will go into node 1 and say visited node 1 equal to 1. So this node is marked visited, and let us say that this is the second node visited by the algorithm. Now what are the successors of 1? The successors of 1 are 0 and 7. But 0 is already visited. Therefore 0 need not go. So the algorithm will now go to 7. So the algorithm from 0 went into 1, and now from 1 there are two successors. 1 has got two successors, 0 and 7. But since for 0 visited is already 1, it will go to 7. So now it will go to 7 and mark 7 to be visited. This is the third node visited. Once 7 is visited, then what will happen is, it will find what are the successors of 7. The successors of 7 are node 1 and node 3. So what it will now do is that since node 1 is already visited, because this checks whether if visited is equal to 0 only, then does it call. So therefore it will not call DFS node 1 again, and from 7 it will call node 2. Once it calls node 2, it will mark node 2 as visited, and node 2 will be the fourth node to be visited by the algorithm. Now node 2 has got three successors, 3, 5 and 7. So node 2 has got successors 3, 5 and 7. But since 7 is already visited, it will not visit node 7. So it will now go to node 3, and node 3 will be the fifth node to be visited. So node 3 is the fifth node to be visited here, and the algorithm, after going to node 3, will mark it and look for the successors of node 3. Who are the successors of node 3? Node 3 has successor 0, node 3 has successor 2, node 3 has successor 4, and node 3 has successor 8. But two of these successors are already visited. So from node 3, we will now go to node 4 only. Sorry, node 8 is not a successor. It had got successors 0, 2 and 4. So it will go to node 4. And node 4 will now be marked visited. It will be the sixth node to be visited. And from node 4, it has got two successors, 3 and 8, of which 3 is already visited. So from node 4, it will go to node 8. So these are all the nodes that are visited till now. It has now gone to node 8. After it has gone to node 8 is the seventh node to be visited, and it is marked visited. After node 8 is visited, then it goes back, because all the other successors of node 8 are already visited. Therefore, the algorithm will now backtrack and go back. So from node 8, it will go back to node 4. And in node 4, so from node 8, it will go back to node 4. In node 4, once it goes back to node 4, no other successor is left, so it will backtrack back to from where the DFS was called. It will go to node 3. Now node 3 has got all visited, so it will now backtrack to node 2. In node 2, we still have node 5 which is to be visited. So now by the algorithm, DFS will again call node 5, and node 5 will be my 8th node to be visited, and node 5 will be visited. Now node 5 has got two successors, node 2 and node 6. Now node 2 is already visited, so node 6 will be visited. So it will now go to node 6, and node 6 will be visited, and node 6 will be the 9th node to be visited. After node 6 is visited, node 6 has no non-visited successor, so it will backtrack. Now it will start backtracking, and it will backtrack from node 6 to node 5. From node 5 it will backtrack to node 2. From node 2 all successors are visited, it will backtrack to node 7. From node 7 it will backtrack to node 1. From node 1, as we can see, all successors are visited, it will backtrack to node 0. From node 0 it will try to come to node 3, but node 3 is already visited. So it will not call node 3. It will go and try to visit node 8. So node 8 is also visited. So based on this, we have done a traversal of this, and the sequence of traversal is 1, 0, 1, 7, 2, 3, 4, 8, 5 and 6. So this is how the depth first traversal works. If we reorder the successor function, the traversal will be different. I will suggest that you reorder the successor function, or I will make a suggestion for you to try the following as an exercise. Try by starting at node 2. Let us say try by starting at node 3. If you start at node 3, then what will be the sequence? If you start at node 2, what will be the sequence? And so on and so forth. So this is the basic depth first traversal algorithm. It is a foundational algorithm, and this algorithm has applications in many cases, and we will come to them systematically. We now look at the basic traversal algorithm on another example. Suppose this is an example of a graph, as we have seen, that if we start the traversal of DFS from here, then we will visit this node first, this node second, this node third, and the algorithm will terminate. On the other hand, if we start from here, somewhere in this part, then the algorithm will only look at these and terminate. So I will request you to find out that, so for example, if I call it at this node has got no successor. Therefore, the algorithm will just mark this node visited and terminate. Which means that the basic traversal algorithm need not complete the full graph if we use only this portion of the code and call it on a single node. Now, how do we traverse the full graph? All we need to now do is traverse this graph by calling it by a function from the beginning, and then using this we can also do some very important techniques which we shall see now. On the other hand, if the graph was a tree and it is a fully connected tree, not a forest, then if you start, let us say we start from here, then this will be visited first, this will be visited second, maybe this or this will be visited third, depending on the ordering. Say this is visited third, this is visited fourth, this will be visited fifth, this will be visited sixth, this will be visited seventh, this will be come back to be visited eighth, this will be visited ninth, this will come back here, this will be the 10th node to be visited, this will be the 11th node to be visited, this will be the 12th node to be visited, then it will come back here and this will be the 13th node to be visited. So this is how you traverse a graph or a tree. Wherever you start from, the sequence of visits will be different, but if the graph is connected, then all the nodes in this graph will be visited. That is how the algorithm works. Now we come to the application of this algorithm. This algorithm can be used for various interesting purposes. For example, the first thing that we can do is to detect whether there is a cycle in the graph. For example, in this node, we know that there is a cycle. How do we detect that there is a cycle? What is the condition? The easiest condition for us to detect that there is a cycle is that if the node is already visited. For example, if we started here, this was 1, then we came here, this was 2, then we came here, this was 3, then we came here, this was 4, then we came here, this was 5, and then we come back to 0, and we know that there is a cycle like this. So it would be easy for us to say and write a piece of code here saying that if we could try and write a piece of code here, if j is visited, which means if, let me erase this a little. We could write if and mark cycle. But there is a slight catch here, because if we go from 0 to 1, then a successor of 1 is also 0. So we also have to check that if j is visited, but j is not a direct connection with I. So if visited j equal to 1, and we have to see that there is no edge between node and between this j, that j, when we say this, when we are checking for each j, which is a successor of this node, we also have to check whether this again does not go back to a back edge of this node, which means that I will check for cycles to check whether a node is visited, except for those pieces of the code of the node which is back its parent, or which is also a direct connection of this node. I will leave the detection of cycle part to you. This is not the code detection, cycle detection code, and I am leaving it as a small assignment for you to do, to include how we will detect cycles in a graph. Similarly, here, if we start from this node, this is the first node visited, this is the second node visited. Now, this has this as a successor as well as this as a successor. For this successor, when I go, this is visited, but this does not detect a cycle because this is a direct connection. So, I will detect a cycle only if the path through which I have come is not the same as the path through which I am going to go back. So this will be a cycle, whereas this is not a cycle. So I leave it to you to write this piece of code to find out how a cycle is to be detected. The third is that how do I find the path, any one path between I and j? That means while I am visiting, how do I find a path between I and j? Now, in order to do this, we define two kinds of edges. One is called a tree edge and one is called a back edge. And we maintain what are called parent links. So, when I am searching from this node to this node, that means when I am going from a visited node to a not a visited node, then that edge is a tree edge. So, this will be a tree edge. This will be a tree edge, this will be a tree edge, this will be a tree edge, whereas once I go back here, this will be a back edge. So I'm marking the back edges by red and the tree edges by blue. Then again I will come back and mark from 3 I will go to 4, which is a tree edge. From 4 I will go to 8, which is a tree edge. From 8 I will go back to 0, which is a back edge. Then I will come back here, and then again I will get this as a tree edge. Then I will get this as a tree edge. This completes basically my whole search. So I have got 1, 2, so I could mark these as my tree edges, and if I remove the back edges, then this forms a tree, as you can see, without any cycles, and the back edges end up in cycles. So what we could do is, for every node, we could mark a parent node P of a node I. For example, the parent node of 1, P1, is 0. Similarly, P7 is 1. Similarly, P2 is 7. Similarly, P3 is 2. Similarly, P4 is 3. P8 is 4. P5 is 2. And P6 is 5. Now, from the parent nodes that we have, if I have Pi, then once I have a path from any node to any node, then through this depth first search, then by just tracing back through the parent nodes, I can determine the path from the original node. So pathfinding can be done, pathfinding can be done by tracing back from the parent node. I leave it to you to write pieces of code here and pieces of code here and pieces of code here, all these places. I leave it to you to update these pieces of code so that you can now find out, modify DFS search to really find out a path between two nodes by maintaining this parent node structure. As we said before, that a graph need not be fully connected. So an important problem for us to solve is to find out what are the connected components of a graph. So given an undirected graph, our objective is to find the connected components. We know that there are four connected components in the, there are 1, 2, 3, 4 connected components in this graph. So what we do is, in addition to the visited array, which we already had, we declare a new global data which is called the component I. And like visited is assigned 0, all nodes have a component number, and this component number is assigned 0. We keep a basic count to 0 to initialize the global component count. And this is how the algorithm works. The original DFS algorithm does the same thing. So the first thing, I'll come to the overall main algorithm, but first let me discuss the algorithm which is the modification of our DFS search at a node. So this part is same, it marks visited equal to 1. And then it does an important thing that we just used the component function. So what it does is, it assigns component equal to count. And then for each successor which is not yet visited, it recursively calls. So the only addition is that this component of a node is assigned the value count. Now what happens in the main program? In the main program, we know that count is globally initialized to 0. So what it now does is, for each node k, as we saw in DFS, it may terminate by not visiting all nodes. So we want to ensure that it visits all nodes. So that is why before calling this, and once it comes out of this, we have a global loop by which we say for every node k, if visited k is not equal to 0, we increment count and call the recursive algorithm. Sorry, this recursive algorithm name will be dfcomp, because this is dfcomp, this is dfcomp. So now what happens is that, let us see how it works. Let us see how this ensures that we have the component numbers done. So let us work on this example that we have. So suppose we start with this node, node number 1. So node number 1 is marked visited, and so for each node k, so let us start with node 1. Visited k is 0, so count is 1, and we call dfcomp. So now count is 1. So now we are going to mark two values. One is whether it is visited by a circle, and then whether the count value, the component value, we are going to give the number. So here component value will be 1. Then let us say this node will be visited. Component value will be 1 because it goes on, the component value does not increase. Then let us say this node is visited. Sorry, this component value is still 1. Let me erase this. So this component value is 1. Then it visits. So after it comes here, it visits this node. Its component value is 1. Then it comes back and visits this node. Its component value is 1. It visits this node. Its component value is 1. It visits this node. Its component value is 1. It visits this node. Its component value is 1. And the algorithm will complete. This part will come out. And it will go back because there is no other connection from here. And all these are the same component, connected component, and all have been labeled 1. Now it will go to node 2 is visited, 3 is visited, and so on and so forth, till it comes to node 9, which is this node. Node 9 is not visited. So it will check node 9 is not visited. Now count will be incremented by 1. Count will become 2 and it will call node 9. So this node 9 will be visited. This will be incremented by 2. This will be visited. This will be incremented by 2. Next, it will complete because there is no other node to be connected to this. So it will come out and go back here. The next not visited node is node 11. So it will go to node 11, but before that it will increment count to 3. So node 11 will be visited, count will be 3. Then the next node will be visited, count will be 3. Then the next node will be visited, count will be 3. Again it will come back and then it will call node 14, but before that it will increment count to 4. So by this algorithm, as you can see, we have identified 4 connected components. And the count value that we have is the component number. Now let us look quickly at the complexity of these algorithms. The algorithms are very simple. The algorithms visit every node exactly once, because if it is visited, it is not checked, and therefore it traverses every edge exactly once. Therefore, the complexity of these algorithms are of the order of V plus E. So these are called linear time algorithms and are very effective in rapidly detecting properties that we have just seen, whether there is a path, whether there is a cycle, whether there are connected components. Now we could make this more and more complicated and interesting. For example, at the beginning of every node, we could determine that we have already done a numbering which we showed. So we could do a numbering here to show the sequence of nodes visited. We could also put a timestamp T1 here and a timestamp T2 here to indicate when it enters a particular loop, when it enters a particular node, and when it backtracks from that node. For example, we could find out when it has entered this node, and once it enters this node, from here it will come to this node, then it will come to this node, then it will come to this node, then it will come back here, then again it will go to this successor, do this whole part, come back. So there is a timestamp of entering this, there is a timestamp of doing all this and going back to this. So these two timestamps also give various properties of the graph, which we shall see. I will request you to start reading about depth first numbering, and entry exit timestamps, and it is used for various other methods, algorithms, of which one very popular algorithm is called finding the bi-connected components. We will do these numbering and other things in more details later on, but I'm just giving you an idea, and I would request you to update this piece of algorithm, piece of code, to look at bi-connected components. We could also do BreadthFirst Search. So how does BreadthFirst Search work? Whereas DeptFirst Search is the recursive algorithm using a stack, BreadthFirst Search is an algorithm which uses a queue to maintain the sequence of nodes visited. So what it does is, it has a global queue. It has a global queue which is initially empty, and you call it with BFS a node, any node k. It marks k equal to visited and puts k in the queue. This is the start node from which the BreadthFirst Search starts. After that, it performs the following. It checks whether the queue is empty or not. It removes the first element of the queue, and for this element of the queue, it checks whether it is visited or not. If it is visited, it does nothing. If it is not visited, then it marks it to be visited, and for each k in successor j, it puts it into the queue. So if this node which has been removed has already been visited, it does nothing. Otherwise, it marks it to be visited and enqueues it. There are various other ways in which you can do it. This is one way in which you can do the search. So let us see how the algorithm proceeds. Let us say we start from 0. So then the algorithm proceeds like this. So initially q is node 0 by this method, by this part. Then 0 is removed because all visited are marked initialized to 0. 0 is removed and 0 is marked visited. This is the first node that is removed. Then what happens? Each successor. Who are the successors? 1, 3 and 8. So this is removed from the queue, and then the queue becomes 1, 3 and 8. And then the algorithm again goes back here, because this is not a recursive algorithm. Among this, again it goes back, queue is not empty, so it dequeues this queue. Which element gets removed? This element gets removed. So it is marked visited, and this is the second element removed. Once this is removed, then what is put back into the queue? 0, 7 and 2, because all successors are put back into the queue. Here, what we could also do, for each k in successor j, we could also say if visited k if visited k is equal to 0, then only could have enqueued q. If we did this, then we would not enqueue 0, we would enqueue 7 only. So the next step, the queue would become 3, 8 and 7. Because it's a queue, it will enter at the end of this. So now this is visited. Now what is removed? Something from the beginning of the queue. So the next node that is going to be removed is going to be this node. Once this node is removed, which successors are going to be put? 0 will not be put, 2 will be put, and 4 will be put. So the queue now becomes 8, 7, 2 and 4. Again, the whole thing proceeds. From here, we remove the first element of the queue. So the node that is going to be next removed is 8. So the sequence of node removals will now be 8. And once 8 is removed, only 4 is already added to the queue. So 4 is added to the queue, 0 is in the queue, all are visited. So no new node is added. So we have 7, 2 and 4. After this, 7 is removed. So 7 is the fifth node to be removed. After 7 is removed, 2 is already in the queue. So no new node is added to the queue. And the queue now becomes 2 and 4. This is how the queue works. This is step 1, this is step 2, this is step 3, 4, 5, 6. This is how it is done. Next, in step 7, node number 2 is removed. It is the sixth node to be removed. Once 2 is removed, 5 is added to the queue, and therefore we have 4 and 5 in the queue. After this, node 4 is the seventh node to be removed. In the next step, we have the queue only having 5. After 5 is removed, 5 is the eighth node to be removed. In the next step, the queue has got node 6. And then 6 is the ninth node to be removed. And therefore, in this step, Q becomes null. And once Q becomes null, the algorithm terminates. So as you can see, depth-first search has a particular ordering which goes deep down. Breadth-first search has an ordering similar to this. It goes like this. It goes breadth first. And so on and so on. So a frontier is created in breadth-first search, whereas in depth-first search, this method moves in a different direction. Both of them are of the same order of complexity of order V plus E, but both of them, in terms of their numbering, in terms of their properties, have got different properties. For example, we could maintain the parental links, and while in depth-first search, the first path that you get from a node to another node is not necessarily the shortest path. If you use breadth-first search, the first path that you get is the shortest path in an unweighted graph. Now let us come to a weighted graph. If a graph has got weights, then how do I find the shortest path? If I use pure breadth-first search, then the shortest path is not necessarily obtained because a path may be of length 2 but cost 25, whereas a path may be of length 3 but cost 5. Therefore, just enqueuing and dequeuing will not work. I am just giving an idea today. We will discuss this in more details when we discuss finding the shortest path. But just to give you an idea, what we need to do is order the queue in order of the costs of the path of a node that it has been obtained and update the cost of the path whenever you find a new path. I have written down this algorithm. I will request all of you to study this algorithm, go through it in details, and then it will be easier for us to discuss this algorithm. This sort of an algorithm which we are going to do to find the shortest path in a weighted undirected graph or in a directed graph. For example, a directed graph can be considered to be an undirected graph. An undirected graph can be considered to be a directed graph with both usages. This leads to a very, very famous shortest path algorithm called the Dijkstra's but we will not do that today. There are other problems also to find what are called all pairs paths or transitive closure. That means we want to simultaneously find out whether there is a path between any pair of nodes, or we want to find out all pair shortest paths. All these we will do in subsequent classes. This class was an introduction to two of the basic traversal algorithms, depth-first search and breadth-first search. And then we will see how these traversal algorithms are useful in developing some very complex solutions to some very important problems. I will request you to go through the depth-first search and the breadth-first search, go through the depth-first numbering, time-stamping that I have mentioned, examine what we have written in this algorithm here for weighted graphs in addition to whatever we have seen. Please send us your queries in terms of your questions that you may have. And from the next class onwards, we will move on to traversal of weighted graphs and how traversal of weighted graphs can lead to several algorithms. Thank you very much. Please send us all queries that you have. We will have an interaction session later. Thanks a lot.